So, several interesting facts. Sometimes the base of an exponential function does not have to be an integer. Uh, what I mean by that is that it can be this concept which pops up later on. It becomes an irrational number. So, irrational number bases. There are several bases for exponential functions that we model. Two of the most common ones that you'll hear often about are pi as a base and e. Well, pi is approximately 3.141592654 and it keeps going to an infinite amount of times. That's what makes it irrational. It doesn't ever stop. E, and basically E is often called Euler's number, and basically it revolves around banking. It pops up a lot in differential equations and complex analysis. Now, what is so fascinating about E is that not a lot of people know about it. Especially in high school, you're kind of thrown the number around, and you're like, hey, this E appears out of nowhere. Why is this guy doing E? Why is he putting this thing and calling it a number? Well, E is approximately equal to 2.7. And what happens is you have this 1, 8, 1, 8, 1, 8, 1, 8, 1, 8, and it appears as many times as you want it to. And then at the very, very end, you get a 2, 8. And that bar means it just keeps going. Well, what's really weird is these bases can sometimes appear in exponential functions. So what if I had a function of x equal e to the x? Or, more succinctly, what if I have a function of x is equal to pi to the x power? Well, essentially, what we can do is we can do a table of values. Okay, we'll do -2, -1, 0, 1, and 2. And we've got x, and we've got f of x equals e to the x power. So what happens here is I get e to the -2, which becomes 1 over e squared. I get e to the -1, which becomes 1 over e. And I get e to the 0. Anything to the 0 power is always 1. That's right. E to the first power is equal to e squared. Well, that's just e squared. Anything would be an approximation, okay? So some people will be like, round off to the nearest 10th value, round off to the nearest 100th, 1000th, 10,000ths, 100,000s, so forth on. Well, I don't like doing that. I always like using it in whatever my base is, because to me these are actual numbers. Well, for pi, it's the same thing, okay? X equals -2, -1, 0, 1, and 2 for my list of inputs, and we'll go ahead and do 3. And our function of x is equal to pi to the x power. So I really get pi to the -2 power, which equals 1 over pi squared. I get pi to the -1. Anything to the -1 is 1 over itself. Pi to the 0 power, anything to the 0 power is 1. Pi to the first power equals pi squared, pi cubed. As you can see, both of these bases are greater than 1. For certain, e is definitely greater than 1, so obviously it is growth. Pi is also greater than 1, so obviously the model would be growth. So I hope this helps. But basically, what happens is a lot of people are really just introduced to this one a lot because it deals with natural processes. It deals with, it's also called the natural number. E, or Euler's number, is called the natural number. And the reason why is because money grows naturally, people grow naturally, people behave naturally. So, as a result, a lot of things that are in applied mathematics and deal with analyzing nature or our surrounding all deal with this number, be it money or some natural process we view out in the real world. A lot of people will see that number pop up. So that's why this number, the base, e to the x power, is so important. Well, for mathematicians and physicists, this number pops up. So it is kind of interesting. There is, I call it the great schism between applied mathematicians and mathematicians. Here you have all the physicists and mathematicians that basically deal with complex analysis, and then over here you have all of the people like epidemiologists and statisticians and financial analysts that will deal with that number. So I call it the great schism of mathematics between sciences and what I like to call human-based sciences or human-focused sciences like finances, economics, stuff that basically analyzes human characteristics versus physical characteristics of our universe, which is the red one, and the human characteristics of how we act, and the red universe would be the blue one. There are multiple bases. If you can find any constant irrational number, and there are many, phi, the golden ratio, is often called an irrational number. Basically, anything that has growth, like seashells, biological processes, a lot of biologists will come across and try to model exponential functions with phi. I would hope, anyway. I'm not purely a biologist. I just know it's that phi can have some application within biology in representing symmetrical growth of certain aspects of the cell during meiosis and mitosis, and the splittings of cells. So I hope this lesson's been interesting. I hope it helps you understand how we can apply exponential functions even further. In the next lesson, we will go on to talk about transformations or horizontal vertical translations that can occur. Basically, I'm going to just give you a basic algorithm that basically shows you no matter what, you can always move a exponential function. So, until next time.